It actually means duckbill platypus in Russian. It's a really long story. Come ask me after my talk. But today we're going to be talking about comparing malicious files and a little bit about who I am. I'm the former director of research at Threat Connect, and now I'm an independent malware researcher, kind of a Ronin. So to start off, I want to go over some of the problem statements. So when you're comparing malicious files, you might have a couple of different problems that you run into. One of the largest ones that I can identify is what we call the AV problem. So many AV vendors use different nomenclature depending on whatever signature set they have. They might have their own internal signature set, their own internal nomenclature for what the malware is that it's identified. So these are not all overlapping, and some of them are radically different. Some of them use the same systems, so that causes a problem. You also have the marketing problem, which is slightly related to this. So marketing departments want to come up with a cute name for malware. We see this a lot in vulnerabilities. Each vulnerability now has to have a name. By the way, in one of the groups I'm in, I thought maybe Mitre should actually just roll the dice and come up with a 2-syllable name that every CVE is assigned to take away the ability to name things from companies. But maybe that's a solution, maybe not. Kind of like hurricane naming. So what you end up with is rocket kittens and bears and pandas and all this sort of stuff. And then you get this massive group of names which are not necessarily the same thing, but they're Venn diagrams that are all the circles are just slightly off around one sort of thing. And so you've got like APT28, Pawnstorm, Fancy Bear, Sednit, Czar Team, TG4127, Group 4127, Strontium, Tag 0700, Swallowtail, Iron Twilight, Group 74. All of these are approximate synonyms depending on which company you're buying your stuff from. So the marketing problem is a bit of a difficulty. So then from the person who's actually comparing malicious files, I've kind of identified two kind of general roles that they fit into. So when you have all these marketing systems, one of the things that Robert M. Lee noted here is this is the outward-facing piece of the information that you're getting. So what's happening under the scenes is that you have a set of collection criteria where you're basically collecting data from various sources and then organizing it into groups. And so you group it via different features of the malware, different static features of the malware, attribution knowledge that you might know from either the infrastructure or the targeting and stuff like this. And when you reuse these names that other organizations are using as their outward-facing names for stuff that is fully baked, let's call it, you're missing those basic collection criteria that they're using internally, which are typically their intellectual property, and they're not going to share those basic criteria with you. And what I mean with those basic criteria is you've got just a plethora of data coming in from all of your collections, and then you're basically bucketing it into buckets. And these buckets don't have fancy names. They'll have a numbering system or lettering system or combination of such. And so once you've got a bucket that becomes, a little bit more coherent and people, your analysts start focusing on it, that can be promoted into a more formal name, and then marketing gets a hold of it, and then that thing starts attacking important companies, then it becomes a cute name. So the problem with using these is you don't know the criteria that are being used under the hood. And so it's always good if you're going to do this sort of thing, if you're going to compare malicious files, just use your own system, develop your own system of basic criteria, collect and create your own bucketing system, and focus on groupings that come together and become more coherent the more data you have about them. So there's two general groups of people. So you have the researcher, like myself. We have a little bit more of a relaxed aspect of what we're doing because we don't we don't have an emergency that's going on. We're just looking for new things. So one of the questions you want to ask is, what is it I'm looking at? What malware family is it? Can I relate this to other samples that have already been identified? And, basically, is this something new? Is this something that I could publish about? Is this something that I could talk about that is something that is completely different or slightly different than things that have been discovered before or found before? Is it a new attack? Now, the things that you're going to do to identify and compare malicious files are very much the same, but the other person is the incident responder. So an incident responder is under the gun, basically. You have an incident. You have to figure out exactly what this thing is that was on that workstation, that network, that router, in this organization, and you have to do it as quickly as possible. So identifying other samples that are related to it is not necessarily for the same reason that a researcher would, but what you want to do is find other research about this particular unknown and then basically take a shortcut in your research so that you can figure out exactly what it is as quickly as possible. So if you have an unknown, it might be a waste of time to go and do a full reverse engineering on it if you can identify other related files that may have been already reverse engineered by someone else or have been researched by a different organization. So finding those and identifying something as quickly as possible is more important for an incident responder. So as far as solutions to the two different problems, the two overarching problems, how to identify a file and how to find more files that are like it. So sample identification is basically determining the malware family membership of the sample. So I say malware family here. There's a couple different sort of overlapping definitions of malware family. You could think of it as, some people would think of a malware family as something being used by a particular threat actor. Some people might think of a malware family as being just the structural, the static values of the file, static features of the file that, tie together a particular build of software, for instance. And some of it just ends up being a TTP, or a collection of techniques and tactics and how that particular file is used to attack someone. So the other piece of the other solution is locating associated samples and finding more files that are related to the file that you're looking at. So what you need here is a body of data, other files, collected files from various places, either your own repository or public repositories or paid repositories, and you take the file that you're looking at, gather some features or behavior or data about that, and then compare those to your data set and see if it matches up with any known files, and then you can pivot from that to research that has been done on those particular files. Or you might find a new nexus among files. So the first identification method that I want to talk about is based on antivirus scanner results, and so this is going to be the weakest data set, I would say. You're relying on a lot of different AV vendors and what they think something is at a particular moment in time. The signatures change. If you look at the detection overall of a particular file from all the AV vendors, some of them will change the name of the signature that matches. Some of them will stop detecting something. Some of them will start detecting something. So it's a bit of a messy data set. But I'm going to try to give you a better way to look at it and a methodology to look at it. And a couple of people asked me if I have, they'd seen my talk at B-Sides Charm. So there's actually a new piece of software that I'm going to show you in here, which actually automates all of this. And it's open source. So one of the things you need to look at with using this data is shared engines. So a number of AV companies have shared engines, and you'll see this where the result, and this is actually just a generic Trojan, but if you look at the digits at the end, the 404, 37, 487, compared to the AV scanner results from all of the other vendors in the data set, it's fairly unique. So you'll see these repeated patterns across AV vendors that share engines. And so if you think about it, if you're ranking what you think a particular file is by what the AV vendors think it is, you shouldn't count all of these shared engines as multiple, points towards it being a particular thing. You should lump them in and correct for that when you're doing your analysis. So there's another piece here, and I'm not sure that there isn't just two kind of competing business reasons to go in different directions here. So you've got generic beer, a generic signature, which covers lots and lots and lots of malware, but it comes back as saying generic or Zeus or something like this. And the goal of the companies that are producing this type of signature would be to just block the malware, right? So if it doesn't have a good granular name in the AV results, that might not be the goal of that company. The goal of that company might be to block it completely. But then you have very specific, AV results. So I have my favorite beer company, DC Brau, and so the very specific results might be due to those particular companies having a draw or a business reason to have very granular results. And so those two development methodologies for signatures may have different costs involved, and there might be different draws due to their customer base. So you end up with a variety of different AV vendors which have different results. Some of the vendors I want to highlight that have very usable results, Microsoft, if it can detect it at all, has a very, very specific name for most things that it detects. ESET, Kaspersky, Sophos, these are other good ones that have fairly specific granular results, and I've listed a couple of the malware encyclopedias where you can take the result and look up what they think it is and get a little bit more context behind it. So first I want to show you how to boil down some of the results. So this is a sample you could follow along with on your own later. And what you want to do first is remove things that are clearly generic results. It'll be obvious, generic or gen and stuff like that. But you also have some of the sneaky generics. There are, Zeus, Zbot, Zeusy, a few other groups of names which are no longer really that particular malware family. They've just grown into something that's much more generic, and so are less valuable for identification purposes. So you want to remove the clearly generics and remove the sneaky generics. So here's a data set where I've already removed all of the sneaky results and all of the generics. And you'll see here, these are all one particular shared engine. And then down here, we've got another shared engine. And I'll go back to this one. I know there's that B in parentheses there, but I'm going to count that as the same engine. It's just a little bit of, magic sprinkle that Emisoft has put on their particular AV result, but it's pretty much the same engine. So I would count them all as one. So after boiling down the results and removing all of the other pieces, you end up with these two. So these two, if you look at it a little bit closer, those are approximately the same. So, maybe you give it a half point together, or maybe 1.5 points. And by the way, this is a little bit of a plastic procedure here. And then you have three different engines that have isbar, so we would weight this as a little bit more isbar, a little bit less simi, but simi and isbar. So I know you're asking me, you're thinking to yourself, like, how can I actually operationalize this? So this is the software that I was introduced to recently. So this is an open source project called AV Class. I have actually written my own algorithm in Python for doing this whole similar thing, but just as things go, this is much better than the stuff that I've written. So I'm going to kind of look at the source code that they've got and kind of add any knowledge that I've got to it, and deprecate my stuff. So what it can do is give you family ranking. So like I said in that previous slide, if you go back here, the family ranking would be a little bit more isbar, a little bit less simi. And then it has PUP classification. So if anyone's familiar with PUP, if you're in like malware analysis and stuff like that, it's that sort of gray area. It's called potentially unwanted programs. These are, in my opinion, it's all malware. It's all black and white. There is no PUP. But PUP is more of a legal category, let's say, because the malware author in this case actually has a company and has a presence where they've convinced some people that they have some value. And so, this would be like a toolbar that you get installed that kind of is adware or is spyware, this sort of thing, where it's in that sort of legal gray area where it's not completely malware, not stealing your bank account information, but is a way for you to lose privacy in this sort of thing. Again, this has ground truth evaluation, so you can create a little table if you know in advance that this particular file belongs to a malware family. You can preload that into a configuration file, and then you can compare your ground truth with what AV class comes up with after boiling down AV results. It also has generic token detection, which is what I mentioned earlier about removing the generics and removing the sneaky generics. And then it also has alias detection, so you can take the different AV company names and you can create synonyms for them. So you can create aliases. So take a look at that. It's basically a full product for doing exactly what I've been talking about up until now. So another identification method is Mitre Attack, and so Mitre Attack has it's basically a set of tactics and techniques, and it's a data set where you've got a detection method. Usually, there's a way to detect the thing or that tactic or technique. Usually, there's a signature in pseudocode often, and so this is an excellent first step. But for malware classification, it's not really ready. And I actually spoke with some of the people that are behind Attack after the last talk, and there's actually a better option. So Attack is good, but there was the MAEC or Mike, which is malware behavior, and so there's a new a rebooting or a new refresh of Mike, which I'll go over in just a moment, which is more appropriate for malware classification specifically. So if you think about it, Attack is more adversary behavior, and then Mike is more for behavior of a malware file, so automated behavior, as opposed to adversary behavior pivoting around the network and doing their bad stuff. So one of the complaints that I had with Attack is the lack of granularity now. It's not going to be this way for as long as people keep contributing to it, but it doesn't have a lot of granularity. So what you're looking at here is a malware campaign called Alpha Blend. That's the blog post I wrote about it. And what you're looking at here is called a structured exception handler. So a structured exception handler is, who here programs in Python? All right, so this is pretty easy for me to convey to the people that write Python, or if you're already a programmer, you know what an exception is and an exception handler. But in Python, you have a try and accept statement. So if you try something and then it causes an error and then you catch the error in that's the exception handler. And then this is where the adversary puts their code in that exception handler, and what they do is they, instead of catching an exception that they think might happen, they do something that forces an exception to happen, and then it passes execution away from where that exception happens over to the structured exception handler. So it makes it slightly more difficult for someone to reverse engineer it. This is an anti-debugging technique. And so even though the structured exception handler can happen in many different ways, and then the malicious code might be very different, there's kind of two signposts that you have with structured exception handlers. Up at the top, you have the structured exception handler save, and so that is the push dword to pointer at the top, which is in red. And then you have a sh init, which is down at the bottom, which is the move dword pointer from EAX. And what I found was that the EAX is slightly different than the signatures that I was able to find online. So I did a little search when I was researching this malware, and I found a YARA signature set which actually detects structured exception handlers of this type. However, that YARA signature was looking for a different SEH init. And so right now, this is the second SEH init pattern that I've found. But one of my goals coming up is to figure out, are there other ways to do a SEH init, and then from that SEH init differentiation to see, to differentiate among inside of malware families or among malware families what SEH init they particularly use. So it's just a way to get even more granular differentiation among files. So this is a next iteration of the YARA rule that I wrote. The original author was Naxinez, and so these are the two strings now that match up with. So this is actually the hex of that SEH init. And so if you look at the top, I've actually added a few pieces of attack. So I've started putting in tags in my YARA rules that line up with the tactics and techniques from attack. And then there's another concept called sub-techniques, which attack is working on deploying, which are making the techniques even more granular. So I hope that everyone in the room, if you have time and resources, please contribute sub-techniques to attack. This is the link that you should follow if you want to contribute more things to attack. And so let me give you an idea of things that you could contribute. So this is an example of something that I found. So second factor interception is T1111. And so second factor interception can come in many different forms, right? And so these are sub-techniques that I have, I've got a set of documents ready to submit to attack about these. So second factor interception can happen as SMS interception on the wire. If you're familiar with SORM, which is the Russian universal data collection system, there have been examples of people who have used SMS-based second factor going over Russian networks, and then the SMS is intercepted and then used immediately to log into their, whatever they're logging into. You can also have SMS interception by number porting. So this is if you have your phone number gets ported to another SIM card by an adversary, and then they collect your SMS and then log into your stuff. You have the more older forms of SMS, second factor interception, code interception via phishing page. So these are Nile, Fish, and Charming Kitten commonly use these. If you look at some of the research that's been done on them. And then the sort of least common denominator is keylogger. So there's a lot of green space in attack for you to contribute and make it more granular and make it better. So another thing I was talking about earlier is the better Mike. So Mike has been rebooted, and for malware behavior, this is much more appropriate. So this is actually where a lot of my research and data is going to be steered towards now. So the new Mike, this is the link for it down at the bottom. They have a malware behaviors taxonomy set, and so these are the basic components of the taxonomy set. And as you noticed earlier, the SEH and anti-debugging, that's something that's actually captured here in the Mike malware behaviors rather than attack. So you've got anti-behavioral analysis, anti-static analysis, and that's actually where that structured exception handling, identification fits. And please go look at this. And again, if you're more interested in the malware aspects of things, please contribute to it. So another identification method is called Melpedia. And so Melpedia is a site that has many contributors at the moment. It is a closed system. It's an invite-only closed site, but the stuff that is exposed on the outside is the ability to look up YARA signatures that you can use to identify different malware families. And you basically take a file and then you send it to Melpedia, and then all of the YARA signatures that they have in their library, any of them that match the file, will trigger a string match, and it'll show you if the string matches on one of their rule names or multiple rule names, you'll get a result back based on which rules were triggered, which is very powerful, but it doesn't necessarily have critical mass quite yet. You'll notice that there's three different things. You either have reference samples that are the ground truth known to be that particular malware family. You have signatures, and then you have information about who's using it or what malware family or what adversaries are. So there's plenty of gaps that the people that are running Melpedia and Melpedia needs help filling. So there's plenty of work to be done. And this is another thing I've added to this to the talk. You can actually submit changes or propose changes in Melpedia on your own, even if you're not in the invite-only group that runs the system. So if you see something that you want to add to it, proposing a change for some of the adversaries, behaviors, malware samples, etc., you can actually add that yourself. So please contribute again. And then the least common denominator is Google. So if you have something that you need to research, like even a file hash, Google it. Because as we all know, the way that you become an expert in IT is, finding a menu item, buttons, blah, 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 blah. Google the name of the program plus a few words related to what you want it to do and follow any instructions. So Google is still a very powerful tool. So if you've seen some of my earlier talks about this subject, I had a proposal for fixing kind of the nomenclature problem, but I'm going to admit that my proposal was incorrect. So my proposal was basically to use the idea that biology has already, the binomial nomenclature. And I was thinking that binomial nomenclature, if applied properly in malware identification, would work. Because first of all, it gives the marketing departments a little bit of their fame piece, because they still get to name something after themselves or after their favorite book or whatever, as biologists do with new species. But the problem is that isn't going to really work, because there are so many different layers of how you identify a malware family. And from the adversary level, you have the botnet operator, you have the person that wrote the software, the author, you have the distributors. You may actually have the same piece of malware may have multiple different personas operating on it at different moments in time. So an implant an implant in an organization might be sold by one adversary to a different one. They might have one adversary goes and infects a number of hosts and then groups those together and sells that to a different adversary. You also have a malware family where maybe that particular file, the change in the command and control is not based on any structural change to the file, but it's a change in the configuration. So that we'll have a command and control packet or configuration file change, and now is that a different malware family? Is it not? And so you also have the idea of what's called an intrusion set. And so an intrusion set is a tool. So these are like the hacking tools that don't count as malware, but are always bad if you find them on your network, but they're not actually malware, like Nmap, for example, and this sort of thing. So these would be a tool, and then you have the malware, and then you have the adversary, the entity that's controlling it. So the collection of these things, along with the TTPs, like how that whole thing behaves, is called an intrusion set. And so the intrusion sets are more important to kind of differentiate than it is to kind of differentiate all the different malware families per se. So perhaps my proposal was incorrect, but I'll be seeking, always looking for better ways to kind of differentiate and compare malware files. So for association methods, I want to go over a few basic ones. So one is static analysis. So when you're reverse engineering malware or analyzing malware, there's a few different stages of the analysis process, and you have automated analysis. And in automated analysis, you have static analysis, which is looking at the features of a particular sample. And then you have behavioral analysis. And so behavioral analysis is where you run the file. So static analysis, you're not actually running the file. You're just looking at its structure. And then behavioral analysis, you're running the file and seeing what it does in the operating system, what activities it has. And then you have manual analysis, which is going into a debugger and basically full reverse engineering. So that's where you sit there and step through the malware using a debugger, or if you have another instrumentation system, but you're actually manually observing and watching the file as it runs. So for static analysis, some of the basic pieces of static analysis that you get back are hashes. And some important hashes, in my opinion, are these two. So ssdeep is context-triggered piecewise hash. And so ssdeep, if you think of the regular hashes like an MD5, SHA-1, SHA-256, you've got a sample, and that sample, without a collision, let's just exclude the idea of hash collisions. But you have a file, and that equals one hash. And then if you change the file even slightly, you get a different hash. So identifying groups of malware, that's not an ideal type of hash to use. It's impossible to use in that way. It's more for differentiating two files that are exactly, very, very close together. But ssdeep, what it does is it takes your file and essentially breaks it up into equal parts, predetermined parts, and then hashes those parts in a certain way so that you can take two files and you can see which part is different, and you can basically see how different two files are, and it's called an edit distance in particular for ssdeep. And so ssdeep doesn't necessarily tell you where you should put your threshold. So if you've got a set of files, let's say X group of files, and then you've got one file, you would get an ssdeep edit distance between each one of those files. So some of them are a little bit further away, some of them are a little bit closer. And so when you're using ssdeep, you need to pick a threshold of how close of that edit distance would you consider same. And so you'd basically you'd pick a good edit distance that you would consider same, and then all the results that are inside of that edit distance you're going to then look more closely at. So this is a way of kind of shaving down the extra information, additional information when you're looking at a huge data set. You can narrow it down to something that is more manageable for you to do further, more specific investigations on. So one of the problems that you'll find with ssdeep is that most of many of the repositories of malware out there are not unpacked. So malware is usually put into a packer, which can be a commercial packer, like something that commercial software uses to package their software. It could be something that just encrypts it. It could be something that compresses it. So if you're applying ssdeep to a repository of files that are packed, you're going to basically compare the edit distance between the packer, not the payload. So you need to, if you're using ssdeep, it's much better to unpack all the files and then apply your ssdeep process to the unpacked file. So essentially unpacked would be, for example, if the malware runs, unpacks itself into memory, you want to take that, you want to capture the code that's actually running in memory, the unpacked code, and apply your ssdeep hashes to that. Import hash or imp hash, this is another very, very powerful hash. So PE files have an import table. These are the functions that are imported for it to use. And so that table has a certain order and a certain set of imports. And so if you take that import table and create a hash of it, you can find other files that share that exact same import table. And there's a high likelihood that those other files are related to the file that you're looking at. And again, from a large data set, if you find a set of files that have the same import table, that smaller number of files gives you a manageable number of files to do research on and target and run through either automated analysis or manual analysis. But again, there's a couple of sticky points with import hashes as well. And And some malware is packed with .NET. And so if you pack malware with .NET and you look at the import hash of the resulting binary, you're going to find an import hash that's shared among lots and lots of other .NET binaries, and you're not going to identify it as being related to your file, you're just going to identify it as being .NET. So another wealth of data is from EXIF metadata. These are some of the highlights. So the modified time, so any of the times that you can get out of a file are very effective data points. And then the modified by and the author, these text strings are other things that you can use to identify out of a large data set files that are related. Again, up here, code page, so languages other than English. If there's a different code page outside of the usual ones, that's another one that can be used as a single data point. Code signing certificates are very important. So you'll find fake certs, self-signed certs. You'll have stolen certs that are taken from a legitimate software company that have begun, then they've been used to sign malware. And then you have these sort of outliers, which are who knows what the heck it is. It's not a cert, but it's in the correct directory under the PE file for it to be a cert, but there's actually something else there, maybe ASCII art or something. Who knows? But all of these I would consider certs in some way, and all of them, even the ones that are broken, can be used if you find another file and that cert is broken in the same way. Those two can be related together. I found over the past few months a particular malware family called FileTor, which is doing a really, really bad job of, or good job of abusing certificates. So of these, approximately 25,000 samples, there are 500 legitimate certificates that were signed by CAs. So these, the malware authors actually went out and purchased certificates, signed their malware and sent it out. In a previous talk, I actually called software signing certs. I had a Freudian slip and just called them malware signing certs. So moving on to a couple other data points. So you have PE metadata, so sections, imports, exports, resources. We saw the power of imports earlier. So these are all components of a PE file. I know this is a little bit hard to read, but a PE file is structured in a very regular way. So you have directories and areas in the PE file that are always in the same spot. And so you can take things like sections and resources and take that smaller set of data and make a hash of it, and then you can find other files. As long as you've repeated this process across all the PEs in your repository, you can find other files that share that same section or share that same resource. So here's an example of a resource, so reloc, and this is the MD5 of this particular section. Again, here's a resource, so NT version, and that's the SHA-2v6 of that area of the PE file. There's also a few sort of algorithms that allow you to take a file and find other ones that are related to it in various products that companies have. So Reversing Labs, this is the Reversing Labs hash algorithm. They've nicely written a blog post about exactly how they do their hash algorithm to compare files. Another one is VirusTotal. They have an index called similar to. It's quite powerful. They create what's called a vhash, but it's proprietary black magic, but it's super effective. Document metadata. Again, back to those strings that we just looked at in the EXIF tool. You have author, timestamps, language, PDF producer. In the PDF land and the Office document land, Office documents, they call it author. PDF land, they call it PDF producer. But that's basically the name of the person who, in theory, created that document. Now let's talk about dynamic analysis. So there's a few interesting components of dynamic analysis. So you've got file names. Just the file name, if the file name that the particular malware drops itself as or drops pieces of it as, if it's all the same, it's not really important. But it's more exciting if that malware actually has an algorithm for generating random or seemingly random file names. And so you can write a regex if you know that pattern. You can write a regex, and the particular pattern of dropped file names that the malware uses can be used to identify the malware family. I put this in here just because it's interesting. It's not necessarily related to identifying the malware family, but the place where the payload is stored, like the compromised website. Compromised website, the structure of that URL is closely related to the vulnerability that was used in compromising the website. So that's not related to the malware family, but I figured I'd put it in here because I'm talking about URL structure anyway. So this is an example. You'll see compromised websites with the payload or the phishing kit or the malware, whatever, stored in something like WP content, themes, 2016, 2015, 2014, 2013, et cetera, et cetera, et cetera. So you can build a regex which would identify that particular, the particular vulnerability, WordPress vulnerability. So keeping that in mind, let's think about C2. So the command and control infrastructure for a particular file has, it's directly related to the malware family. So the C2 structure that it uses is actually encoded in the malware file. And so that's under the control of the malware author, and it's the way that the file calls back to its masters. And so this is directly related to the malware family. So an example of this, this is, I believe, if my memory served me correctly, this is a Pony sample. And this is Pony password stealer. It's a fairly common type of malware. And so it has a very regular gate.php and then a string before that. And so you can differentiate certain builds of Pony depending on the structure of its C2 callback. And by the way, this Zapoy is, so this is actually Russian, and so Zapoy basically means bender, like a drinking bender. But Zapoy is usually not like a weekend, like a drinking bender. It's more of like a month or 3 months long Zapoy. So a mutual exclusion. So mutual exclusions are used to prevent race conditions. So if you have, in the multiprocessing and multi-threading world that we're in now, when you write software, you have to kind of deconflict what the software is doing across processors and threads. And so the mutual exclusion is used so that these software doesn't stomp on itself by being run in different processors or run in different threads. And so malware authors also need to use mutual exclusions. And so it's a string that's used to kind of deconflict. And that string might be unique by the malware family. So observing in the malware behavior the mutual exclusion that it sets can show you other malware families that use that, or other malware samples that use that exact same mutex. So that's a good way to identify. Registry keys, so the registry behavior. Almost all malware is going to go and make many edits, create registry keys, delete registry keys, adjust registry keys, updates, all this sort of thing. So that set of changes that the malware does to your registry can be used as a signature to find other malware that does that same set of registry behaviors. So let's go a little bit more high level and more complex of association methods. So there's clustering algorithms. And here I'm actually going to kind of stand on the shoulder of a giant. So this is Seb Draven. I would point you towards his talk. This is from 2017. I was at botconf and I took this workshop from him. So it's Python and machine learning. And one of the things you learn is how to take there's a public data set and then apply a few of the common algorithms like k-means and dbscan to take a file that you have and then compare it to a repo of other files and clusterize them and see which cluster it fits in, which cluster your file fits into, or which cluster it doesn't fit into. And what's interesting about this is if you take a look, you would think, oh my gosh, if I'm going to clusterize lots of malware files, I need a GPU, I need like all of this horsepower. But there's a concept called sparse matrices, where you can actually save a lot of your computing resources by using sparse matrices to clusterize malware, and you can actually use a laptop just like this to run, as long as your data set is reasonable size, to clusterize that data set. So another association method is the diamond model of intrusion analysis. And so this is an example of the diamond model. I know this is the technical track, but I'm going to throw in a little bit of Star Wars. So this is an example of the diamond model applied to Star Wars. So the diamond model has the adversary, so this is the attacker, right? And then you have the victim. And then you have capabilities. So capabilities are the malware or the implant of some type. Infrastructure is where everything calls back to. And so if you group your samples and your information and data into these areas, you can then see patterns like the victimology, who the victim is compared to the adversary, and the callback infrastructure, and then the malware. All of these can be used to relate the different these groups together and kind of learn more about the relationships. I invite you to go ahead and go learn a little bit more. Go to that is the actual diamond model paper. And another association method is Icewater. So this is basically a clusterization algorithm. You can do a search in here. So if you have a particular file, you want to generate a hash, do the search in the Icewater hash search, and you end up with clusters, and then you have the cluster neighbors. So you have the blue cluster, which is the cluster of the thing that your file is a member of, and then you can see all these other clusters that are 1 bit in that cluster ID. These are 1 bit different, and then the green one is 2 bits different. So you have a cluster, and then the green one is a cluster of stuff that's 2 bits different, and those big orange ones are clusters of 1 bit different. So this is a way, if you have a file, you can then find more files that might be either a different build of the malware family, etc. So you have more data to look at. And it also produces a nice little picture, and so if you take a cluster and you take all the pictures, you can make a little movie, and you can see exactly where the thing is changing inside of the cluster. Control flow graph analysis is another methodology. So this is another one where I'm going to point you to someone who's much smarter than I am. So take a look at Douglas Goddard's talk. This is the YouTube video of it, DerbyCon 2014. If the camera was slightly to the left, you'd see the top of my head. I was in the front row, fanboying. And so control flow graph analysis is essentially where you take all of the blocks of code and look at the control flow. So control flow is either an if-then, where it changes to a different block depending on what the variable is set to, or it has a loop. So loops and decisions like if-then are all control flow. And so if you take all of those blocks and then take all of the different decisions that it makes, you can create a signature based on that control flow. And so adversaries are going to reuse their code because all programmers are lazy, and that's a good thing. That's a positive quality in programmers. And so when you reuse code, you've got, you may have one malware family that was written by a particular author, and you can see that control flow in a different piece of software that may, within a certain confidence, be written by the same individual, or at least copy pasta of that same code. And the last thing is graphing threat data. And so this is, if you know sticks, this is one of the kind of nomenclature. So you have sticks domain objects, and these are all the different pieces, malware families, indicators, attack patterns, and then you have relationship objects. So if you think about it, this is just graph data. So graphs are nodes and edges. So a node is like a data point in that in your data set, and then the edges are how those data points are related to each other. So there's tools for saving that graph data. So you have resource description framework and JSON for linking data. I'm going to kind of breeze through this a little bit because JSON for linking data is not necessarily as important. RDF NQuad is the one that I use. It's a little bit more complex, but the reason for using it is I use dgraph. So these are the two major graph databases today. Neo4j is a little bit older. I use dgraph because it's much simpler. It's distributed. It's written in Go. It's the hipster graph database. But I would encourage you to take a look at like how this works, because if you think about threat data, it is all kind of naturally already graph data. And so putting it in a graph database is the right place to put it. And if you're interested in graph theory, this is a good book to start with, Introduction to Graph Theory by Richard Trudeau. And then just, so you get a little bit of visual on what this is before I take some questions. So this is a network graph. You've got a node, and then those are the edges. And edges can have directionality going, from one to another, or they could be bidirectional. And so this is a network graph of a particular two malware samples. Those are the ones in yellow, and this is a Neshta malware family. So that blue is the Neshta malware family node, and then green is the import hash that these two files share. And then setup.exe and install.exe are nodes meaning the file name. So I just got the finish up message. So if anyone has any questions? So that's actually, this is just the visualization so dgraph has a front end. If anyone's familiar with Elasticsearch, so you have Elasticsearch, and then you have the front end, which is Kibana. So in dgraph land, you have dgraph and then Ratel. What you're looking at here is Ratel. So this is just the way that Ratel visualizes the edges. So that's a bidirectional edge. And the little tilde, those are actually the names of the edges. And so the little tilde is kind of the reverse edge. So you have a left to right edge, let's say, and then the tilde is the right to left, or sorry, left to right and right to left would be the tilde. So the tilde is the opposite directionality. Yes?
Do you ever find a problem on a social level with shared engines? And so a lot of people say there's a false positive, and a lot of people look at that. People walk around on that shared engine find the vulnerability is a false positive, then every single one of them says it's a false positive. And place the result. Do you ever see a problem with that socially?
Not sure what you mean by socially, but let me kind of restate the question. So you're asking if you see a shared engine, have a false positive, and then that detection is removed. Does that cause a problem? Yes. So, I mean, that would actually cause a much more expounded problem if one AV engine that doesn't have a shared engine detects something that isn't actually malware, and then it becomes a false positive, and they remove that. If one of those shared engines detects something, and that's a false positive, yeah, that would compound the problem of that false positive by, times the number of AV scanner engines, times the number of customers they have, et cetera. Yeah.
Thank you.
All right. Thank you, everybody.